Let's start with a general overview of MRI. The single steps of an MRI examination can be described quite simply. The patient is placed in a magnet, a radio wave is sent in, the radio wave is turned off, the patient emits a signal, which is received and used for reconstruction of the picture. Let's take a look at these steps in detail. What happens when we put a patient into the magnet of an MR machine? To understand this, it is necessary to at least know some very basic physics, even though this may seem to be boring. As we all know, atoms consist of a nucleus and a shell, which is made up of electrons. In the nucleus, besides other things, there are protons, little particles that have a positive electrical charge, whatever that may actually be. These protons are analogous to little planets. Like the Earth, they are constantly turning or spinning around an axis. Or, as one says, protons possess a spin. The positive electrical charge, being attached to the proton, naturally spins around with it. And what is a moving electrical charge? It is an electrical current. Now, you may remember from your physics at school that an electrical current causes a magnetic force, or magnetic field. So, where there is an electrical current, there is also a magnetic field. Thus, the proton has its own magnetic field and can be seen as a little bar magnet. Let's review what we have learned. What happens to the protons when we put them into an external magnetic field? Normally, protons are aligned in a random fashion. This, however, changes when they are exposed to a strong external magnetic field. The protons, being little magnets, align themselves in the external magnetic field like a compass needle in the magnetic field of the Earth. However, there is an important difference. For the compass needle, there is only one way to align itself with the magnetic field. For the protons, however, there are two. The protons may align with their south and north poles in the direction of the external field parallel to it, or they may point in the completely opposite direction, antiparallel. These types of alignment are on different energy levels. To explain this, a man can align himself parallel to the magnetic field of the Earth, in other words, walking on his feet. Or he can align himself antiparallel, in the opposite direction. Both states are on different energy levels. In other words, need different amounts of energy. Walking on one's feet is undoubtedly less exhausting, takes less energy, than walking on one's hands. Naturally, the preferred state of alignment is the one that needs less energy. So, more protons are on the lower energy level, parallel to the external magnetic field, walking on their feet, so to speak. A smaller number is on the higher energy level, antiparallel, walking on their hands. The difference in number is, however, very small and depends on the strength of the applied magnetic field. To get a rough idea, for about 10 million protons, walking on their hands, there are about 10,000,007 walking on their feet. The difference 007 is probably easy to remember, isn't it? let's take a closer look at these protons. We'll see that the protons do not just lie there, aligned parallel or anti-parallel to the magnetic field lines. Instead, they move around in a certain way. This type of movement is called precession. What type of movement is precession? Just imagine a spinning top. When you hit it, it starts to wobble or tumble around. It doesn't, however, fall over. During the precession, the axis of the spinning top circles, forming a cone shape. Protons, in a strong magnetic field, also show this wobbling type of motion, which is called precession. In real life, this is a very fast movement. For reasons we will learn later, it's important to know how fast the protons precess. This speed can be measured as precession frequency. That is, how many times the protons precess per second. This precession frequency is not constant. It depends upon the strength of the magnetic field in which the protons are placed. The stronger the magnetic field, the faster the precession rate, and the higher the precession frequency. This is like a violin string. The stronger the force exerted upon the string, the higher its frequency. It is possible and necessary to precisely calculate this frequency. This is done by using an equation called the Larmor equation. Omega 0 equals gamma B0. Omega 0 is the precession frequency in hertz or megahertz. B0 is the strength of the external magnetic field, which is given in Tesla, T, and gamma is the so-called gyromagnetic ratio. The equation states that the precession frequency becomes higher when the magnetic field strength increases. The exact relationship is determined by the gyromagnetic ratio gamma. This gyromagnetic ratio is different for different materials. For example, the value for protons is 42.5 MHz per Tesla. It can be compared to an exchange rate, which is different for different currencies. It's now time to take a break. However, let us briefly review what we have learned up to now.